Welcome to this episode of Eureka. We are going to have a very wonderful conversation with Dr. P Sreekumar, Director of Indian Institute of Astrophysics, one of the earliest institute which have worked on astrophysics and astronomy in India. Before we continue with the conversation, let's take a quick look at his brief profile.
Professor P Sreekumar is an outstanding astrophysicist who played a key role in Chandrayaan-1. Presently, Professor P Sreekumar heads the Indian Institute of Astrophysics in Bengaluru, where he remains firmly focused in promoting India's endeavours in space science and technology. He obtained his PhD in physics from University of New Hampshire, Durham, US, after completing his MSc in physics from IIT Mumbai. After 10 years as a research scientist at NASA's Goddard Space Flight Center, Professor Sreekumar has been head Space Astronomy and Instrumentation Division from June 1999 to December 2009 and Group Director Space Astronomy Group from 2010 to 2013 at ISRO Satellite Center, Bengaluru. Since 2013, he has held the position of Director, Indian Institute of Astrophysics, Bengaluru. His research interests include high-energy astrophysics, extragalactic gamma-ray background, X-ray studies of Sun and the solar system, astronomical instrumentation and X-ray optics. Professor P Sreekumar has more than 120 publications in refereed journals, and apart from this, he has also received various outstanding awards like Chandrayaan-1 Payload Team Award in 2009 and NASA Group Achievement Award in 1991.
Thank you for being with us. I mean, you had a wonderful profile with, work in various places, various institutes, and finally you are the director of this institute. And you had a research career, I think, which spans more than 4 decades. So suppose if I ask you, list 3 of your, let's say, most passionate or more favorite projects that you are involved in, what would you? I'm sure there are many more, but for want of time, let's say if you limit it to 3, what would you list them as? 1, 2, 3.
So one of the first ones that I worked in the area of high energy gamma ray astronomy. So these are looking at photons that are very, very energetic. To give you an example, it is something like, a billion times the energy of a photon that our eye is sensitive to.
Okay.
So this is an area of astronomy that has been very rarely explored, and in the 1990s, just like the Hubble Space Telescope exists, there was another mission of NASA called the Compton Gamma Ray Observatory, the second great observatory of NASA. This mission had a role to really map the sky in gamma rays, and I was fortunate to be a member of the science team at that time during my phase there. And one of its key objectives was to really look at what the sky looks like, and as in many areas of astronomy, we will find point sources of emission in the universe, which were then later understood to be active galaxies, quasars, in the very distant parts of the universe. And they also found a faint glow. That was one of the findings in the specific area that I worked in.
I think in those days, people used to call it as something like the glow of the universe or something, right?
That's right. There is a very familiar glow called the microwave background, which has been studied from the 1950s onwards. But there was a prediction that such glows would exist in gamma rays as well, and we had the first opportunity to look at this glow in gamma rays. So the objective was to characterize this glow and really make sure it is indeed a real emission. And I spent a good fraction of time working on this issue, and we produced one of the first spectrum that actually showed what this glow is all about and its uniformity across the sky. And the second part, of course, was to try to understand this glow as whether it is arising from unresolved sources because our telescopes are not sharp enough, and so objects can look fuzzy, and that can actually add up to the glow. So that was one of the major findings from that experiment, as to really show that such a glow exists, its characteristics we known, and then the scientists spent many scientists in many areas looked at trying to explain this glow, right from the fact that the glow could be produced from point sources, or it could be something of cosmological origin. A second important area that I feel very proud of was at the time when I was with ISRO, and we were looking at, I had shifted from gamma rays to maybe something closer to the solar system. We had a great opportunity to fly experiments on the first lunar mission, Chandrayaan-1, and I was fortunate to be there at that time, and we had a couple of experiments that I was directly associated with, and one of which actually involved a collaboration with the Rutherford Appleton Laboratory to look at the chemistry of the surface of the moon.
Now, chemistry of the surface of the moon. But Chandrayaan mission had only one small lander. The rest was actually going around the moon, right? So how do you study the chemistry without actually landing on the moon? I mean,
so for any planetary mapping, but in this case chemical mapping, or the ideal orbit really, ideal position to measure it is actually from the orbit itself.
From the orbit itself?
Orbit itself, because if you have a polar orbit, the moon rotates under that, and we can actually over some course of time cover much of the surface of the moon. So this particular experiment relied on the fact that the sun, which is not a very steady object in the sky, is very violent and often produces high energy photons in X-rays. These X-rays, which are produced during a solar flare, would strike the surface of the moon, excite the atoms on the surface of the moon, and produce, when these atoms de-excite, they produce this fluorescence emission, where the emission characteristic is tied to the element itself. So there is a direct...
So which means that if there is a particular element, if it is stricken by a X-ray, it will emit a glow in a particular kind of frequency.
It's a one-to-one mapping between the emission that we see, energy of the photon that we see, and the composition or the element that releases this photon.
Okay.
So this is fairly well known in the lab. But today on Earth we do a lot of these experiments. You know, if you go to a goldsmith, you actually see they derive how much copper and how much gold is there using fluorescence. The only difference is we try to do this with natural remote sensing technique, where we can't take an X-ray source to the surface of the moon. We use a sun, and then you do it. And the challenge, of course, was that the sun is not a steady source. Sun varies, and it's what it produces is unpredictable. When it produces unpredictable, so we have to be prepared all the time. So when the sun flares, we also make a direct measure of the sun's emission, and then look at what comes from the reflected emission from the surface of the moon, and then with some theoretical modeling, we are actually able to derive what is the composition of this surface of the moon.
Very, very interesting. Okay. What was the kind of third work, I mean, particularly?
The third work is something that I'm now currently involved in, and that is, I've been involved in the first India's astronomy satellite, AstroSat. We had an experiment that was had brought in for the first time X-ray optics, the capacity to image X-rays, to focus X-rays. X-ray focusing is completely different from the way optical photons are focused. We have to use what is called grazing incidence optics. This was developed at TIFR, and there's an experiment on AstroSat called SXT that uses this. Now our objective is
just for us to understand this better, see, when I talk about light, I can have a material like, say, for example, glass. And if I shape the glass like a parabola, I mean, if I make a mirror of a parabolic size, if I shine a light on it, it will focus on the focus. But X-rays are supposed to go through almost every object, right? So how do you actually focus them? I mean, that will be a major...
yeah, it's a very fair question to ask. What happens is X-rays have this unusual property that it's the refractive index at X-ray energies of most materials is very, very close to 1, and sometimes less than 1. And once it has such a property, it actually doesn't, the only way to make it reflect is through what is called grazing incidence. You allow the X-ray to come at a very shallow angle, at an angle where between the surface and the X-ray photon, the angle may be less than half a degree. And then it produces a focus as it bounces off, something like what is familiar in total internal reflection, except in this case it's total external reflection.
It's something like, say, for example, children play, you take a small stone on a pond, and you throw it at a particular angle, the stone jumps instead of actually falling into the water.
Correct. At a shallow angle, it scatters off, and you get what is, using the lattice structure of the material, it actually produces a focus, and that's how you do the X-ray focusing. So what we now embarked is an attempt to really improve upon this, not so that we can push this energy to this capacity to higher and higher X-ray energies. So to do that, typically if you use the same techniques, you really have to go to shallower and shallower angles, which then means the mirror, though geometrically big, effectively becomes smaller and smaller and smaller.
Okay.
So the technique around it is to actually build what are called multi-layer mirrors. You allow the X-ray photon to reflect off multiple layers, and numbers can exceed up to 100, 200, 300 layers, and each layer produces a constructive reflection, which is then collectively picked up at the focus. So these are called multi-layer mirrors. So we're right now involved in this activity of trying to combine the resources at the BARC's Raja Ramana Center for Advanced Technologies in Indore, and colleagues in the ISRO Satellite Center and at IAA, to really do design of such systems which are effective both for soft X-rays, hard X-rays, as well as for X-ray polarimetry. X-ray polarimetry is a very important and emerging field, and we're just having the first of these X-ray polarimetry missions coming up, through a satellite that ISRO has now approved for launch in the next few years, but its capacity is limited. We want to go beyond that, and this development is something that I hope will take it much further.
Very interesting. So, which essentially means that the next generation X-ray telescopes is on the cards, and most likely we should be able to build it almost indigenously, with resources being pulled in from our institutes across the country. That's a very interesting point. We need to take a very short break. Don't go away. We are going to have a very interesting conversation after the break. There are projects which are going to take our satellites to sun. We are going to watch the sun on a regular basis. Maybe the next advanced solar telescopes is going to be there somewhere in India. We are going to have lots of discussion about big projects which are coming into India. Keep watching Eureka. We'll take a very short break. Don't go away. Welcome back to Eureka, and we are having a very wonderful conversation with Dr. P Sreekumar, Director of Indian Institute of Astrophysics, Bengaluru. Thank you for being with us, and we had a wonderful conversation about your work in the past 30-40 years. But let's now shift to the kind of work that is taking place in India. You are heading a very major institute which is involved in astronomy and astrophysics, and today India is embarking on very many major projects. And one of them is apparently a solar telescope, which people are talking about placing somewhere in Ladakh. After all, one of the earliest solar telescopes have been under your institute in Kodaikanal. So why do we need this one? Why can't we use that?
Now, as in all areas of astronomy, there is a greater and greater thirst for higher resolution, better sensitivity, more frequent observation of the celestial object as much as we can, because science is improving, theoretical models are improving in a manner that we really want to understand how many of these features that you see on the sun, for example, evolve in time, how are they connected to other processes that we observe, and so on. So to improve upon this capacity to really address these theoretical problems that are set out, we want observations that are comparable to these things. So we begin with small telescopes, as we said. We did have a very important contribution from the Kodaikanal Observatory using very interesting telescopes. The tunnel telescope still operates for daily observation of the sun. We have a 100-year history of actually observing the sun, and today that data is publicly available for people to study, look at the long-term evolution of the sun, connections to various other physical processes and so on. But to improve upon this, we need larger collecting area. So we need to really have mirrors that are larger. Today, India has largest solar telescope we have here is a 50-centimeter telescope. Recently, that has been erected at the Udaipur Solar Observatory, and now functioning well and doing very interesting images of the sun in specific narrow regions of the sun, looking at sunspots. Sunspots are important. Sunspots evolve at a rapid pace. It has something to do with the space weather. We need to be understanding the physical processes that are behind it and so on. So what is being proposed, and right now it's only at the proposal phase, is a 2-meter class solar telescope, which the Indian Institute of Astrophysics had led this effort some 4 or 5 years ago to propose it. We have done some homework in the past. We need to find sites that are appropriate for it because it's a daytime telescope. Turbulence in the air is a big concern. So you often, as you would notice, solar telescopes are typically located in the middle of lakes where the water provides a free a laminar flow which actually prevents turbulence, and hence the sharpness of the images are substantially enhanced. So we've been searching for such a thing. We have done a lot of homework on this, and we have now come up with sites in the country, in the Ladakh region, that are actually very suitable for these issues. And we have now been doing analysis that actually looks at what type of telescopes to be put in, what should be its mount, what are the instruments that go with it, and so on. Solar physics has dramatically improved in the last 15 years, largely from the fact that space plays a big role in this. So there's been a lot of space-based telescopes that have been positioned in locations that are appropriate for solar studies, that has improved its capacity. But to put a 2-meter telescope in space is a very expensive proposition, very difficult, and so there continues to be complementarity between space and ground in actually pursuing science of this type.
I think now ISRO is also thinking at putting something called Aditya in space, right? I mean, where your institute would also be involved. So how does that connect with this land-based telescope which is being proposed in Ladakh?
The primary instrument on the Aditya L1 mission is a coronagraph, which is being built largely at the Indian University of Astrophysics in collaboration with many ISRO centers. This particular instrument focuses on studying the solar corona. The question is, what heats the corona? Corona has a temperature that's much greater than what is the surface of the sun is, and when the source of heat is at the center of the sun, always the concern has been, how do you heat the corona when the surface is only at 6,000 degrees? This question of solar coronal heating remains, and so this instrument is designed to look at the corona as close as possible to the disk of the sun.
Okay.
Now, considering the tremendous contrast in the intensity between the disk and the corona, typically you see the corona only during a solar eclipse, we want to create artificial eclipses. So we create on this coronagraph a mechanism to remove the disk light by largely reflecting the image of a sun through a mirror which has a hole in it. The hole is as large as the disk, and so now what the mirror reflects is only the corona. So this coronagraph, its challenge is to really come very close to the disk without taking the disk light. Now that's the real challenge. This would be one of the unique experiments in actually bringing the study of the corona very close to the disk. So technically very challenging. So it tells us something about what happens in the immediate vicinity between photosphere and the corona. So coming close helps us in this issue.
What are the major mega projects on astronomy and astrophysics where, as India, as your institute, we are engaging with?
We are indeed I would say, a golden age of astronomy if we look at capabilities that are coming up in the future. One of the key projects that the University of Astrophysics is involved in is the 30-meter telescope project, which is a global project to look at, to build the largest telescope on ground. And this is a consortium of many countries. India is partner in that. India has roles where we bring in nearly 70% of the contribution in kind, which means the work gets done in India in partnership with other institutions, in partnership with companies and private industry that exists in the country. Some of the key areas that we contribute to are, this is a 30-meter telescope, has a 30-meter mirror that is made up of nearly 500 segments. So each segment is roughly about 1.4 meters in diameter, the hexagonal components, and of these nearly 500, about 100 of these are going to be built in India.
Okay.
So we're building the infrastructure, we're building the capability to have these mirrors built. A building is coming up near Bangalore, in another campus of the University of Astrophysics, which I hope will become a facility on which we can build our own indigenous 10-meter class telescope on a segmented mirror design. We are also involved in actually looking at the elements that make these mirrors connect together as a continuous single mirror system, which means a control system that goes with it. One of the key elements of that is a sensor that tells how far is an edge of one mirror from the edge of another mirror. These are called edge sensors. In working with our industry, we have now designed edge sensors that are being fabricated, that meet the specs of the project's needs, and we'll have to make a fairly large number of these things for the project. We're also building actuators that actually move these mirrors every second typically to correct for small deformation that could arise from other disturbances, including wind effects, when the telescope is observing. And we also build the structure on which these mirrors are being mounted, called segment support assembly, for all the segments. So there's a fairly large number of hardware elements coming from India, in addition to software.
So which means that this collaboration, we are not just only giving money, but we are actually participating in building it.
Absolutely.
We'll discuss all these things after the break. Keep watching Eureka. Welcome back to Eureka, and we are having a very interesting conversation with Dr. P Sreekumar, Director of Indian Institute of Astrophysics, Bangalore, which is part of Department of Science and Technology. We had a very interesting conversation. We had talked about your work, then we talked about some of the major projects that we are going to embark on, including the 30-meter telescopes. These all major projects would require a huge amount of indigenous capacity building, right? I mean, we need people who can actually use this. It's not like we are going to build it and somebody else is going to use it. So we need to develop human resources in this country. What are all the major challenges in that segment?
What you said is absolutely right. Our capacity to participate in such large projects really depends on the ability to actually generate a partnership between the academia, the industry, and young students who are going to come into this system. We have been, as part of some of these efforts, already recognized, and including the existing mega projects. We do see that we are now discovering many more members in the private industry whom we never knew about, who have the capacity and capability to actually contribute to these issues. So I hope that's a rising trend and we will be able to maximally utilize that issue. The need to collaborate across institutions is something that has always existed, but I think these bigger projects are forcing us to really do that in a real term and in a real manner, and we are actually now able to enable that. There's a lot of cross discussions and interactions, which I think is a good sign that I hope will allow us to do many more joint projects with just within the country as well as global programs. A third major component is actually this making sure there is a stream of youngsters who enter the field who has academic interests, who have the interest and the capability to actually work with experiments and industry to enabling many of these technologies. This is an area that we have some concerns on. We are not seeing as many of the youngsters getting into experimental sciences. This may have to do with various factors, but there is a need to enhance it, and as an effort we have actually initiated a program in the Indian Institute of Astrophysics for the last 5-6 years, which involves engineering students coming into what are called pure science areas. So we have BTech students who come in and they enter a program which is a joint program of MTech and a PhD, which the University of Calcutta is actually involved in. Conducting the first year teaching happens there. The second year onwards they get involved in projects, and many of them are actually now involved in many of these mega projects, and I see a great hope that many of them can actually indeed contribute to multiple mega projects, because with their core engineering skill and their renewed interest in sciences, I think we have a nice mix of people who come in. But that still doesn't leave out the need to have regular physicists and astronomers who enter the field to really work with not just their data, not just with theoretical equations, but go beyond that and actually also work in being able to enable and organize and plan many of the new projects that are coming up, on which I'm very sure opportunities are immense, given the great talent that exists in the country, the number of people that we have in the country, and the solid foundation that has been built up over many years. So the ability to manage this resource would actually determine where we go in the future.
That's an interesting point. Coming to the other issue, which I think is something that as Indian academia we need to face, is when you get into this kind of big projects. The earlier way of each institution working in silos cannot perhaps continue. We need to reinvent ourselves, work in collaboration even within the country, not just outside. And we should be actively looking for collaborations from outside rather than just coming and looking at us, right? So how do you face this kind of challenges?
It's a very important point, and it is indeed something that we have not very actively pursued, that is to go and seek collaborations outside the institutions. I mean, in some areas it has happened, but in astronomy in particular there's a greater need for these things, and very recently we've been discussing how to enhance the capability in the Southeast Asian regions. We're now having more discussions on it, and one of the things that is being currently planned is to have a small delegation that actually goes to neighboring countries, examine their core areas of strength, project our future vision in it, and then look for viable collaborative programs with this. This is something we do need to do on a fairly urgent basis, and within the country, the multiple institutions involved are, in conjunction with the Astronomical Society of India, are in discussions right now in trying to enable such a program to come about.
That's an interesting point, and I think it aligns with one of the key concern that this government is also talking about, using science for diplomacy. That is peace diplomacy, that using science to have interaction with our neighborhood countries. That's a very interesting area, and astronomy and astrophysics perhaps is an area where we can engage without much of controversy or a problem. Coming to the major question that would still remain within our borders, education. Where do you see we need to go if you have to capture all this opportunity which are coming up in terms of this new projects, big projects, new opportunities that we are getting in?
I mean, we do have to motivate our children right from early school days onwards. So there is a greater emphasis in doing that. The professional community may have stayed a little aloof in the past, given their preoccupation with various issues, but given the urgency of this issue, there's a greater emphasis these days to actually take research to the schools. I mean, there is need not be this big gap that existed, so there is a lot more such events that are taking place of trying to motivate the concept of research in youngsters. And the style of teaching, though we are bound by certain regulatory norms, there need to actually have avenues outside the normal classroom for youngsters to really get motivated regarding future opportunities, the pursuit of research, the thirst for knowledge that goes beyond the classroom. It's something as research institutions we do need to do a better job at it, a greater job at it. And so now this new effort, I hope will actually enable youngsters to seek avenues that are beyond the traditional career options that they look for, and the freedom to pursue this is something I'm sure they will, once they get to know of it, they will actually do it. So I have a lot of hope in the fact that as long as we do our homework and actually taking the message to the schools, we will do a great job in actually bringing them to the
And so
focus.
this brings me to the final question of this program. Because of lack of time, we won't be able to continue with many more questions. But then one is, what's your institute offering to, let's say, college students, college teachers across the country?
What we do now, for example, since 1st of February, we will have a series of lectures. There's a 20 lecture series every Saturday at 2:30 in the afternoon when the classes are over, for college students in the city to come and listen to an astronomy series lecture. 20 lectures, and they get a crash course, and they can decide whether to join this field or not to join the field. Either way, it's an important thing for them to do. That's one thing. We are also looking at a set of lectures that are meant for the larger public. Could be on a Sunday when they are free, parents can come with their children. Educating the parents is as important as that, but this is more for curiosity-seeking public. How do you, we have many questions about the sky, about things that happen on the sun or wherever. So that is the second stream we are going to do. At a more serious level, when there are colleges involved, and we have some linkage with some of the nearby colleges, where the students can come and utilize some of our facilities. Now they have been coming and visiting them, and for a day or two doing some observations, but we are now trying to formalize that, under which every month we might allow some time on some of the less used facilities, but still relevant for young students to experiment on. Capability to actually ask for time, actually do real observations, and if those who are really keen to pursue it further, guide them in making some sense out of these observations. I hope this is something that many colleges will make use of.
That's an interesting point. There are three things. If you are a student or a parent and you would like to know what astronomy is, you are curious, they have some programs, use it. If you are a college student and you are looking at whether you can enter into this area, I mean whether the astrophysics is your cup of tea, they have some series of lectures which can give you a crash course, and then you can decide for yourself, is it fitting you? If you are a college teacher or a group of students who want to use some modern facilities to try out some small projects, their facilities are available. With this, we will end this conversation today. But keep watching Eureka. We will come back to you with another episode, with another conversation next week, same time.